All right, class, welcome to our class meeting number 1. As you know, our class meeting number 1's entirely online. We won't be meeting in the classroom on Tuesday. This will be our presentation recorded. What I plan to do is make a recording something like this for all of our class sessions that you'll be able to view and watch online before class meeting if you want. What we will do in the class meeting will be to answer any questions about what this content is or any clarifications that are needed. Again, you can log in through Collaborate for those online classes if you're not in the attendance group, which gets to why I have the course syllabus shown here again. The course syllabus overview was posted for you to take a look at, some additional information in there, so I'm not going to look at all the details here. What I want to go to in the syllabus is this course overview again. Remember that no attendance is required. Everybody is given an attendance group, and so those are the days you can attend the class. In addition to the attendance group, there are going to be 5 standby seats available. So I believe I divided the class into 4 groups, and that still allowed for 5 more people to attend. So I've put those on standby so that if you wanted to attend additional days, more than your attendance group only, you can come in then. All right, that's what that's going to work. Yes, it'll be limited to the 5 first people. What else? I want to look at our competency review assessments. These are going to be online through Blackboard. Those are going to form the content of what we get out of our book and the homework problems. So you will answer those online. That's my plan. So you won't have to submit any document that way. And then of course we have our projects. So the projects are the documents you will submit and work on. I believe project 1 is already posted. So we'll talk more about that in a minute. So here's class 1. We're meeting only online for that. That counts as our Tuesday meeting. And then on Thursday, see if I can highlight that. Anyway, on Thursday, attendance group A can come to class, as well as 5 other people. If you're not in group A and you want to try to come to class, you can. Again, no class attendance is required. The content for class meeting 2 will be posted prior to that class, and you can review it just like this. All right, I won't go through all the details of the syllabus then. I think that is everything. All right, so I'm going to close this, and we're going to start looking at our class content. We'll have the slides and the board notes together, and then I will go over those with you in this recorded session. So I'm not going to be writing the board notes up as we did before, since I can prepare them ahead of time, since all this has to be recorded anyway. So let's just take a look at this. What you see on the board notes right here, I'm going to switch to this pencil tool, see if I can mark that, for example. Yes. So we will be looking at things out of our book that you will be asked to refer to and answer some of those questions on those assessments. Hydrograph, let's get to that in just a minute. I wanted to include here the parts of the book that we will be referring to. These are the 3 main topics, and that's what we'll look at on our class slides. I've included a couple YouTube videos for you to look at. These are right here in our own area. This is, of course, the viaduct down at 3rd Street and Eastern Parkway, and it still is subject to flooding. But this is one of the issues with urban hydrology. And many of you will probably be working in cities and trying to help come up with ways to mitigate this. What are the ways we can mitigate that? It's a very challenging issue. So if you watch this whole video, you'll see, watch the cardinal bird there, you will see that that becomes completely, I'd say about 2/3 submerged. And next time you're out there, you can see how deep that water is. I believe they've got it marked, you just can't see it here. There's another cardinal bird right over on this one. So you see somebody driving their car into the water, and that's partially because it's very hard to tell what the depth of water is when you're driving. So from a transportation engineering point of view, it's important. From a utility point of view, it's important to try to prevent or understand at least how our infrastructure is going to be responding to rainfall runoff. So that's an important thing for us. One old-timer rule of thumb is, and you see this railroad is built way up above, even before that viaduct was in there, that railroad may have been built. And they say that in the old days when railroads were getting put into the U.S., that typically they would be well above the high water marks that were evident to the surveyors that were laying out these routes and elevations for the railroad beds. So if you didn't have any other information on how high to make your roadway, and you wanted to stay out of the most severe floods, you could use those as an indicator. Anyway, I'll let you watch that. Let's go on to the next slide. Here's some more pictures. There are people walking through the water on campus. Here's a car that floated in the water and got stuck on a hydrant. Here's somebody clearing a drain. And here's another video of another flood on campus that was a little bit more recent. And what I'll do, let me just see if I can go to, again, it shows Eastern Parkway here. And this is the modern view. The only thing I would point out to you right there is right here is what we call a pump station. So that pumps the sewage water from the low point onward to the treatment plant. All right, let's go on. How are we going to use information that we have to do engineering hydrology? And the first two slides I've got here are two what we call hydrographs, and I've kind of given them the schematic here on our slide. Flow measurement over time. That's called the hydrograph. So Q is our flow rate, volume per time. And some of the interesting components are everything above this level I've got indicated as space flow comes from the rainfall runoff. So that's the important part. And usually this is what somebody wants to know from you, not what's the base flow, although that can be important if you're doing water resource planning and you need a water supply and you need to know what the lowest is ever going to be for a constant supply. But usually we're doing development and we're interested in this number. What's the highest flow for a given runoff event? And what is this volume of water that is under the hydrograph? So those are the things we want to be able to estimate, and that's what you'll be able to do at the end of this class. Here are a couple natural hydrographs, one from a small stream. This is Mill Creek, which is kind of along the Ohio River in southwest Jefferson County. But it would look something like this. Here is a snapshot of Beargrass Creek near Joe Creason Park. And there is a flow gauge there also. What do we see in these hydrographs? We see they go up and then they kind of come down gradually. Up rapidly, down gradually. This is the typical shape of runoff hydrographs. These flow only due to rainwater runoff usually. Of course, you could think there's all kinds of things that could happen. Some kind of chemical spill or industrial outflow that could cause it. Okay, let's take our hugest river in the U.S., Mississippi, Baton Rouge, all the way downstream. Still, we get a hydrograph. Water goes up, down, so it's a little more gradual here. And the floods last a longer period of time because, of course, this river is draining a huge area. But we still experience the same kind of cycle, just with a different magnitude. And it can also be important to know water levels. If you're a transportation engineer, here's somebody managing barge traffic and the flow of commodities, commercial traffic. And you can see here that during dry periods, the barges can't get through certain sections of the Mississippi River. When that happens, all traffic stops. So it's kind of like the inverse of a bridge going out. So here they don't need a bridge, but they need the water. And when that happens, it can be an issue. So predicting that flow is a very useful transportation engineering thing. All right, let's go on here. What else should you get out of Chapter 1? What goes into hydrologic design? I've listed some things here. Here's a picture out at Shelby campus of a very nice straight long channel. So going back to like Manning's equation, this is something we could readily study, and that might be why it was put in. because it's easy to design the capacity for that. What is needed to design that capacity? So that's what we want to be able to do in this course. We studied that before with Manning's equation, just seeing what is the flow Q that a channel like that could carry. And if the channels aren't designed quite right, we can get this severe kind of erosion. It can even undercut the road or overtop the road and cause the pavement then to slide off. So here are some of the design criteria for rainfall. We need to know what climate we're in so that we know the setting. If we're in a desert kind of geography, we're going to get a different kind of rainfall than if we're here in Louisville, Kentucky. Same thing if we're in a mountainous area. We're going to get a different kind of rain. So understanding that is an important part for doing design, and then knowing also what kind of criteria do we have that we need to meet. So for the runoff, one thing, the rainfall, of course, becomes runoff, but how much of it? That depends on our watershed. So what is the shape of the watershed? What are the number of streams it's got? What are the slopes of those streams? What's the land use there? Vegetation versus impervious areas, and then also storage. And by that we mean if the channel is very windy, we might be able to consider storage because the flow is not coming directly out as in a straight channel like we see on the slide here. And then also the level of safety. If this is an area that can flood and we can allow that to happen, at least at some points, then we need to consider that versus an area where we never want it to flood if it's a public safety issue. So we will be looking at what kind of then formulas have people come up with over time, and what kind of data sources do we need and where do we find it. That's what your projects are going to help you a lot with, is knowing where do I go to get data, whether it's rainfall, runoff, what about design equations, what about acceptable levels of flooding. So those are what our projects will allow. I think I've got another video here. Let's go back over to these slides and see if this one will play. Set the speed up on it also, because this one's a little bit longer. Let me slow that down just a little bit. So here is that typical kind of roadway issue. So for whatever reason, this roadway, the pipe under the roadway either became blocked or it wasn't designed with a capacity large enough, so the roadway started overtopping. And once that happened, we started to probably get severe erosion around the pipe. Now you can see what's happening is eventually that pipe gets washed out. Now why are these issues? Again, public safety here. If this were at night and you were driving on this road, probably someone would not see that that road was kind of at a critical state. So let's see what happens here. So water became ponded basically behind the road embankment, and it didn't have an outlet. So providing outlets for the water and knowing how much water you can expect for a given road is an important issue. So just putting a culvert in of some given size may not be enough. You have to account for where is that culvert located. So it's possible the water flow alone could have passed, but maybe you can see this is in a kind of wooded area, so someone needed to account for the debris from a wooded area getting washed into that culvert, possibly blocking part of it. So I think this is almost done. Yeah, let's just watch, because you'll see that by the time all that water erodes through there goes the culvert pipe. Looks like it could have been large enough, but it's hard to say if it was blocked or there were some other maintenance issues there. All right, so I think they have a snapshot of the road afterwards. Yep, so it became quite a big erosion for that. Just like the one we had on the previous slide. This one was on Brownsboro Road. near Ballard High School, if you're familiar with that. It's all been rebuilt now. All right, let's go on. Next. Yep. All right, so the hydrologic cycle, I think let's go to the next board note here. Trying to make sure we're not trying to spend too much time on these. I'll hope to keep these down to about 20, maybe 30 minutes. So the hydrologic cycle, this is part of chapter 1 content. I'm going to ask you some things about this. This is, of course, just what you would expect. How does water move in the earth? So the important part to note here is how it goes through liquid to vapor evaporation. And then it falls as precip. And it can be rain, snow, ice, any kind of frozen or non-frozen precip. What happens to that? Some of it goes into groundwater, but some of it becomes runoff. And that is really the focus of this course. How much becomes runoff? And how much is the precip for your area? So if we can get those two things, accounting for all of this in between, then that's the goal of our class. And of course, here's a couple other terms. We want to account for what we call losses, whatever goes to groundwater. Some goes to plants if we have those and they're significant. Plants taking in water and respirating, we call that transpiration. There's also direct evaporation of water. If you combine those two together, we use this term evapotranspiration. I've included these slides over here. Note that the slide shown on the right here sets precip as 100, and then all other components of the water cycle are shown relative to that. So for example, evaporation from land is 61, so 61% of precip on land comes from evaporation on land. 39% of that precip is the moisture over land. Note this though, evaporation from oceans is relative to land. You can see that 7 times the evaporation. Precip over the oceans, you probably know this just because of the land versus ocean on the earth. So that is, what does that say, 385, I believe. So it's almost 4 to 1 land over ocean, water falling, rainfall. So then all the other components are pretty much the same. We've got groundwater outflow to the oceans. Then these two lower pictures are from our book. And what they're trying to show you here is what happens to a watershed when you go from natural condition to developed conditions. And so we can see some of the components stay the same. And of course, this is a light cartoon drawing. The mountains still are going to have the snow. We're still going to get infiltration. What they want you to see here is now when you put in impervious areas, we block some of that infiltration, so it's reduced. That gets caught into our stormwater sewer system. Still have evaporation, still can have wetlands, that kind of thing. So a couple other things that are shown here, detention basin, so we'll be looking at that. That's an important part of engineered hydrology. All right, let's go on here. Problem set 1. Let's see if I've got that here for us. Yep. So this I've got it listed here. It says homework assignment 1. I thought I changed that, but our assignment number 1. Let's see right here. Yeah, I've given you this just to get your mind thinking about how we have to analyze hydrology and hydrologic problems. So the idea of that is that we want to look at inflow and outflow, and that's kind of the focus of what we're going to look at here. And also looking at some of the terms and concepts. They seem simple, but you've got to be able, again, to really put a number on doing these calculations. I'm trying to bring up these board notes again so we can look at those. So let's take a look at the assignment here and see what we've got. I've given you this parking lot. We're just saying that it's a speed school parking lot. This slide showed the construction of that parking lot. If it's raining a 1/4 inch, over 4 hours, then I want you to do some calculations on that. The parking lot we're going to say is 1,000 feet by 500 feet, and we want to look at how much water is going to come off of that parking lot. So just to get started, pretty straightforward. This I'm calling it problem set 1 then. And first thing I ask is, what's the depth of rain? So some of the interesting concepts from this is that you're given intensity of rain, not depth. So you might say, well, it's pretty easy for me to know that intensity is depth per time, length per time. So if we want a total depth of rain, all we need to know is the duration of that. Well, that's true. So all of these things come in to play, though, on our terminology, being able to describe what is the intensity of rain versus the depth of rain. So what is the missing thing I need there? I need to know the duration. Is that an important part? Yes, because if the duration is very short for a given depth of rain, the intensity is very high. If the duration is very long for a given depth of rain, the intensity is very low. And that can give then very different results in terms of the runoff. And that's what we want to be able to know. So duration of rain is important. For us here, we are given the intensity for 4 hours, so you can take the product of that and get the 1 inch of total depth. So that is what we would call unit depth of rainfall. We'll be coming back to that because many of our methods, just like we did in structures class with unit loads and looking at deflection, something like that for a unit load, we do the same thing for hydrology. We look at a unit depth of rainfall or runoff for a watershed, and then we can use that as a design method when the rainfall is higher or lower than that unit amount. All right, the second part, sketch or plot the rainfall rate versus time. So we call this a hydrograph or a hydrograph. So all that is a plot. And so I've plotted one of those right here. I've asked you for this one, what does it look like? It doesn't look like what I drew here. It looks different. We were not given any information about how it varies, so we just say that actually we are told how it varies. It says right here that the rainfall has a constant rate of 0.25 inches per hour. So it's the same for every hour. So for hours, if I was to draw, I would just draw a straight line for the 4 hours, and that would be the plot. So note these things. These are part of our quiz online that we have. What's the rainfall volume? Let's go on. Next slide. Just as you would expect, here's our area, a rectangular area. We know the precip depth. If we want our volume of rain in cubic feet, imagine this then. Depth times the area, you're going to get a volume. So the volume of rain, do that calculation. And here's part of what I want you to take away from this is you're going to have to start thinking not necessarily now about the physical properties of water like we did before. Remember the density or specific weight of water. Now what we're going to be working with a lot are land area sizes. So how many square feet in an acre? 43,560 square feet in an acre. How many acres in a square mile? That doesn't come into play here right now, but it will later when we're looking at acres and square miles, because some methods like acres, some methods want us to use square miles. So we have 640 acres per square mile. All right, let's go on here, do the product here of depth and area size. What is our depth? 1 inch. Convert that to feet. How about our area? 500 by 1,000. So I came up with this number. You're going to want to check my number. Convert that to what we call acre feet. So that would be, if we had 1 acre, what would be the depth of water in feet for that? Why do we want to know that? That's a common unit used for reservoirs, detention ponds, that kind of thing. So we want to be able to know that. So if you do that conversion, it comes out to be just under 1 acre feet. Check that out for me. Volume of runoff. It says number 4, if there were no losses to infiltration, evaporation, residual water on the pavement, that's our depression storage, what would be the volume of runoff? Well, if we have no losses, then the volume of runoff is going to be the volume of rain. We just calculated that. This should be volume rain. So make that little cross in there that we know significant sets it as volume. All right, so that's going to be our highest factor of safety. If we take the case that all the rain becomes runoff, then we're expecting the largest kind of flooding or runoff flow that we would get. All right, let's go on to the next one, number 5. How does runoff volume compare for an area in natural or undeveloped conditions? So whenever we have impervious areas, we're going to have higher runoff. So we expect the volume for a paved area to be greater than the volume for an area with pervious surfaces. Natural areas are typically have some loss, some vegetation, some not completely impervious. What about the flow rate? So when we have an impervious area, usually the velocity is faster, so there's less resistance to the flow. Not always, but often. So if the land shape has not been changed significantly. Of course, if we put in an impervious area and we flatten what was a very steep area in its natural form, we may not change this runoff rate as much. So usually, though, the runoff rate is going to be less for a natural area, so slower. All right, and then finally, number 6, the last one. What about the timing of the runoff? So imagine that the flow is going from one corner of this parking lot to the outlet. That would be the longest flow path. If the surface has the same slope across it, we would expect that to take the longest travel time. Now, this is an important engineering design parameter called time of concentration. And some of you who have done hydrology in your co-op may have had to calculate this using a formula or some kind of evaluation. So there are many different ways of estimating it. Most common is the velocity method, where we get an estimate of something like what the velocity across pavement would be for what we would call sheet flow. And you've probably seen this on a parking lot before, a wide flow of water coming down, kind of cascading down across the entire surface. Look for that next time. And you can impress your friends by saying, there's sheet flow versus channel flow, where the flow is very concentrated. All right, what is concentration time? It is related to what we call lag time. So you can imagine water falls on a surface. If you were at the outlet and it started raining, you wouldn't immediately see all that water coming. Why not? It has to travel across that surface. And once, though, it starts traveling from all the points and reaching that outlet, you're getting a lot of water then. If the rain keeps going that long, that flow will be at its maximum when all the water is reaching your outlet point. So that is our point of interest for engineering, time of concentration. So for this example, we just calculate the length. I took the diagonal, came up with this distance, divide by some estimate of the flow velocity, and again, you have an idea of what this should be. Should it be 0.1? Probably not feet per second. Should it be 10 feet per second? Well, maybe not, unless it was very steep. So I picked a number of 2. You could probably argue for anywhere from 1 to 3 or so, maybe 4. So put in your number here. Doing that, I came up with 5:59 seconds. Put that into minutes. I think I asked for it in minutes. Did I? Minutes or seconds? You get about 10 minutes. So maybe that's about right. Our parking lot out here is pretty flat. All right, let's see if we have anything else on today's class. And let me go to the next one. Hydrologic budget equation. We want to look at that. And I want to work this last problem out for you. So that's the last topic of this class. Oh, I included this. If you want to hear something about the hydrograph, go ahead and listen to that. That's a very short video. All right, so let's look at our last thing. Our last thing is the transfer function and hydrologic budget. So because of the unknowns in hydrology, a lot of times we use these what we call conceptual models. And basically there are equations that have inputs and a simplified equation that represents what we really want to know. And then we get the output. And we're unable to capture all the physics that we did in hydraulics because, of course, we're dealing with nature and a lot of uncertainty about information in a vast area, say a watershed, where it has different vegetation, land uses, even the condition of the dryness and wetness, the moisture content is going to influence our study. So what we use is something called hydrologic budget equation. It still applies to this concept of conservation of mass like we looked at in hydraulics. Inflows and outflows, take the difference. And then often in hydraulics we said that was zero. So we looked at inflow equals outflow. Usually not the case in hydrology. We have to account for the storage term. So sum all the inflows, subtract off all the outflows. That's going to give us a change in storage. So whatever didn't flow out accumulates in storage. Looking at problem 112 out of our book. Let's go right to that one. 112, what we're given, and I will share this with you, measured values of rainfall and runoff for a 60-minute time period. What we want to do, and the watershed is 65 acres, what we want to do is look at if you had this much rain coming in and this much runoff going out from the 65-acre area, what would be the net storage? So what is not going out from the watershed? Or what is not enough inflow? We're having more going out. So if we take a look at this, we will be applying this equation right down here. Note we're taking this kind of continuous derivative ds dt, making it into a difference form that we can use. So we look at change in time over change in storage over change in time. So here's the problem: watershed 65 acres. Storage could be anything such as soil moisture, depression storage, could even be a detention pond in there, and vegetation. Here's a little schematic showing the watershed, stream flows out, storage is somewhere distributed through here. We don't have to worry about specifically where it is. Rain is our inflow. So make your table up. I just did 2 time steps here. Initially start with everything is 0. And then in the first 10 minutes, this much rain was recorded, 0.07 inch depth. So this is where these units come into play. Runoff, 2.1 feet cubed per second average over that time period. So for 10 minutes, 2.1. Then compute the difference. So what do we need? We need the I, inflow, we need it as a volume. And then we need the runoff also as a volume. Well, we talked about this rainfall. If you know the depth is 0.07 inches and it's over the area size, you can get the total volume then. So that's what I did. Take the 0.07, convert it to feet, then take the 65 acres and convert it to feet. So that's where that 43,560 comes in again. And you have feet cubed. Do the same thing with the outflow. Now look, the outflow is in feet cubed per second. So we need to multiply by what? The time. So here we've got feet cubed per second. We need to multiply by how many seconds are in that 10 minutes. So we convert that into, well, we could have just done 10 minutes into seconds, but I converted it into hours and then into seconds. That's fine too. And we get these two numbers, 516.5 feet cubed of inflow, and outflow was 1260 feet cubed. So we ended up with this net amount. So outflow was less than inflow. So that would have been our total so far. So it would have been our change is equal to the total. All right, so now let's go to the next one for the next 10 minutes. So delta T for this one was 10 minutes also. I can't write with the mouse so well, but this will do. All right, we get rainfall was 0.15 inches, and the outflow is 9.5, not inches, but feet cubed per second. Do the same calculation, see if you get these two numbers. So again, we still had more inflow than outflow. This was the incremental amount, that we ended up with. 29, 692.5, again, still positive. So now the total storage, we keep a running total. Both of these were positive, and we end up with this one, 44,949 feet cubed. And I think that's it. This last slide, we talked about some of these already, but one of the other problems, some of these word problems ask you to describe factors contributing to uncertainty in hydrology. And so what are some of those? Rainfall varies with space and time for a given rain event. This is again a 24-hour rain over Louisville in central Kentucky. You can see from point to point. We all see this when we check the radar to see if it's going to rain on us today. And then, of course, things we need to account for are soil and vegetation impacts on subtracting rain from what we're going to see as runoff. How will you do that? Some of you probably already know some of those methods from your co-op. We'll be talking about that more. Then what about storage of water also in any kind of depression storage, river channels, man-made or natural, lakes, ponds, that kind of thing. And then, of course, the inability to forecast rainfall to an exactness where you could tell somebody the Eastern Parkway culvert's going to flood in the next 3 hours. So that is something we still are facing. All right, I'm going to stop here.